Good day everyone, I am Nemesio Cruz II from BSPE2C. So we are tasked to report about the faults and faulting, and I'm going to discuss about the introduction for it. So let us first define what are faults. So fault is any surface or zone in the earth across which measurable slip or shear displacement develops. We use the term fault zone for brittle structures in which loss of cohesion and slip occurs in several faults within a band of definable width. So Earth is made up of many tectonic plates. So the plates afloat around on the mantle like ice floats on the pond. So the movement of the plates is incredibly slow. So but since the plates are so big, when they bump into each other or rub against each other, we get massive events like volcanoes and earthquake. And along these plate boundaries, we find faults. So faults are cracks in the Earth's crust where movement occurs on at least one side. So in order for a crack in the ground to be a fault, one side or the other has to move. But sometimes both sides move too. So in order for us to understand why we have faults, so let us discuss um, what causes faults. So we have three stress here that causes faults, which is tensional stress, compressional stress, and shear stress. So faults are classified by how they move, and there are three main types of stress that cause movement along faults. The stress occurs because, as mentioned before, the plates fit together really well but also float around the mantle and rub against each other or bump into each other. So what causes this movement? First is the tensional stress. It is when slabs of rock are pulled apart. So imagine stretching a rope out all the way and then continuing to pull on it from both ends. You are putting tension on the rope because it's being pulled in opposite direction. So the same is true for tensional stress in rocks. So on the other hand, we have compressional stress. It is when the slabs of rock are pushed together. So when stress is pulled apart, compressional stress is being pushed together. So they are literally being compressed into one another. This is like when two cars crash into each other or bump into each other, they are compressed into smaller, crumpled versions of what they were before. So the last one is shear stress. It is when slabs of rock slide past each other horizontally in opposite directions. The rocks are not as much smashed into each other or pulled apart, but their edges slide along each other with a lot of friction. So this is like when you rub your hands together to warm them up. So one hand goes forward and the other goes backward, rubbing against each other. So let us proceed for the fault geometry and displacement. So we have here the important vocabulary. So honestly, there were a lot of vocabulary in the reference book, but we could not include them because it might take too much of our time to discuss it. So we have here an important vocabulary on only. So the first one is the shear zones. So it are ductile structures across which a rock body does not lose mesoscopic cohesion, so that strain is distributed across a band of definable width. In ductile shear zones, rocks deform by cataclysite, so a process involving fracturing, crushing, and frictional sliding of grains or rock fragments, or more commonly by crystal plastic deformation mechanism. So next is the wall and the fault block. So rock adjacent to a fault surface is the wall of the fault. So the body of rock that move as a consequence of slip on the fault is a fault block. So the last one is shear sense. Defines the relative displacement of one wall of the fault with respect to the other wall. That is, whether one wall went up or down and or to the left or right of the other wall. So next is the common types of faults. So there were a lot of types of faults, but we just pick the common faults for this one. So we have normal fault, reverse faults, and thrust faults. And the last one is strike slip fault. So for the first one is normal fault. A deep slip fault in which the block above the fault has moved downward relative to the block below. This type of faulting occurs in response to extension and is often observed in the western United States basin and Range Province and along oceanic ridge system. So as you can observe, the normal fault, it is when the hanging wall goes downward. So the reverse faults are exactly the opposite of the normal faults. If the hanging wall rises relative to the foot wall, you have the reverse faults. So reverse faults occur in areas undergoing compression like squishing. So the third one is thrust fault, a deep slip fault in which the upper block above the fault plane moves up and over the lower block. This type of faulting is common in areas of compression such as regions where one plate is being subducted under another, as in Japan. So when the dip angle is shallow, a reverse fault is often described as a thrust fault. So the last one is the strike slip fault. So a fault on which the two blocks side past one another. So the famous San Andreas fault is an example of a right lateral fault. So this causes by the shear stress also. So let's proceed to the heave and throw. So I just want to emphasize the heave and throw because it might help us to determine the displacement or the dip separation of two masses being separated together. So heave is also basically the horizontal component of dip separation, and the throw is the vertical component of dip separation. So as you can see here, the point B and the point B prime is the distance or the dip separation of the two masses. So we have here the heave, which is our horizontal component, and the vertical component, which is throw. So as you can see, we can solve the displacement by using trigonometric theorem only. So it is important to know the heave and throw of the two masses being separated together in order for us to determine the dip separation or the displacement of the two. Last is the block diagram. So I have here the four important vocabulary words. First is clip. So it is isolated remnant of a truss sheet surrounded by the exposure of the foot wall. The second one is the allochthon. The truss sheet above a detachment is the allochthon. So meaning that is composed of allochthonous rock. So as you can see on the illustration, the allochthon here is the gray area, or the gray shield, the biggest gray shield on the illustration. So the third one is window. It is the hole where erosion cuts a hole through a truss sheet, exposing rocks of the foot wall. So on the illustration, it is more likely look alike. It's like a lake, no? So that's the window. It is exposing rocks of the foot wall. So the last one is thrust fault. It is a type of reverse fault that has a dip angle of 45 degrees or less. So that's all. So let's proceed for the characteristic of faults and fault zones to be reported by my group mates. Thank you.
So, characteristic of faults and fault zones. So, brittle fault rock. It is a product of brittle faulting, tends to break a rock into fragments. So, we classify brittle fault rocks based on whether it is cohesive or non-cohesive and on the size of the fragment that make up the fault rock. So, creation of a random array non-systematic mesoscopic fracture that surrounds angular blocks of rocks create fault breccia. Continued displacement across the fault zone may crush further fragments breccia, or may break off of microscopic asperities protruding from slip surface in the fault zone, thereby creating a fine-grained rock floor that we can call fault gouge. Minerals like quartz or calcite may precipitate out of a groundwater, thereby cementing together rock fragments in the fault zone. As a result, breccia and gouge become indurated. Indurated means that the fragments is cemented together. So, formation of vein-filled breccia. In coarse breccia, the cemented typically also fills vein of euhedral or blacky crystals in the open space between rock fragments, resulting in formation of vein-filled breccia. The third one is a consequence. As a consequence, some minerals transform into clay. The layer of the clay that develops in some fault zone can act as an impermeable barrier or seal to further fluid movement. So, cataclysite. So, it is a cohesive brittle fault rock that differ from gouge or breccia and the fragments interlock. So, allowing the fragments rock to remain coherent even without cementation. In photocataclysite, 10 to 50% of rock is matrix. In cataclysite, 50 to 90% is matrix. In ultra cataclysite, 90 to 100% is matrix. So, pseudoticalate, so it is a glass or very finely crystalline material that forms when the frictional sliding generates enough heat to melt the rock adjacent to the fault. Such conditions occur during earthquakes. Argil scabrous refers to a strongly foliated rock formed by pervasive shearing of a clay-rich or very fine-grained mica-rich lithology such as shale or slate. So here are some classification of brittle fault rock. In non-cohesive brittle fault rock, fault gouge. So it is rock composed of mineral whose grain size has mechanically reduced by pulverization. So grains in full gouge are less than about 1 millimeter in diameter. So like breccia, gouge is non-cohesive. So indurated gouge. So fault gouge that has been cemented together by minerals precipitated from circulating groundwater. Fault breccia. It is a rock composed of angular fragments of rock greater than about 1 millimeter and such as much as several meter across. So fault breccia is also a non-cohesive rock. So vein-filled breccia. Fault breccia blocks that are cemented together by vein material. So another term, indurated breccia, is synonymous. Also, there are cohesive brittle fault rock. So sodoticalate, it is commonly flowing into a crack between breccia fragments or into cracks penetrating the walls of a fault. It is, in special cases, sodoticalate may be several meter thick, but generally it is millimeter to centimeter in thickness. So scaglous, a fault rock that forms in very fine-grained clay or mica-rich rock, and it is characterized by the presence of a very strong wavy anastamosing foliation. As a consequence, the rock breaks into little scale or flaky flakes. So cataclysite, so a cohesive fault rock composed of broken, crushed, or rolled grains. Unlike breccia, it is solid rock that does not disintegrate when struck with a hammer. Slip inside and slip invasion. If slip on the fault takes place by a frictional sliding, asperities on the walls of the fault break off and flow into the opposing surface and wear down. As a result, the two walls of the fault may become smoother and, in some cases, attain a high polish. So, fault surfaces that have been polished with the process of frictional sliding are called slip insides. So, some asperities on the wall of the fault flow into the surface of the other wall, thereby creating a groove lineations and the slickened sides. Resulting in formation of alienated slickened sides, also called slickened lines. Groove groove lineations are not the only types of lineation that forms a brittle fault. Also, some fault surfaces initiated with small lateral steps whose presence give the fault of corrugated appearance. So, these corrugations resemble grooves but can be longer than the total displacement of the fault. The origin of corrugations is not well understood. So, some fault surfaces are coated by elongated fibers of vein minerals, typically in quartz, calcite, and chlorite, whose long axes lie subparallel to the fault surface. So, surfaces containing such oblique pits looks like a cross between stellolite and slip lineation, and though some authors call them slicolites. Subsidiary fault and fracture geometries. In case of emergent strike slip faults like the San Andreas fault, a particularly interesting array of subsidiary fault known as R or radial. The P shear develops. So the clay develops ductile strain before any fracture appear. When the fracturing in the clay begins to develop, the first fractures are short shear fractures that are inclined at an angle to the trace of the true going fault that eventually forms. These short fractures are called R or radial shears. Tensile fracture can also develop in association with faulting, which may occur in the wall rock or in the fault zone itself. A series of parallel tensile fracture that forms within a fault zone defines an echelon array or step array that tends to dilate and become veins. Next is fault-related faulting. Forms that form in associated with fault rocks are called fault-relating faults. If at a later time, folding can no longer accommodate the internal displacement of the block and differential stress magnitude in the block increases and faulting initiates. In some cases, a fault cuts through the folds along the hinge of the fault, whereas in the other cases, the fault breaks through the limbs of the folds between the adjacent anticline and syncline. So it means that at the inflection surface of the fault, these are called fault propagation faults. Bend in a fault codes folding of strata that move past the bend during displacement. Because the moving layer must accommodate the bends without gaps is called fault bend folds. So, fault bend folds means that the form in association with all types of fault, but most of the literature concerning them pertains to example developed along deep slip faults. So, situation in which faulting occurs where a sequences of interlayered weak and strong rock layers is caught between the opposing walls of fault zone. The asymmetry of fault zone faults provides a clue to the sense of shear on associated faults. However, because the hinge of fault zone faults change during the progressive shear, the geometry of a single fault may not necessarily provide the net slip vector. So it can define its direction if measured as slip lineation on a fault surface, but if such lineations are not present, you may be able to obtain this information by measuring numerous faults with a range of hinge strengths using a technique called Hanson slip line method. The sheet of rock above a attachment fault may deform independently of the rock below. The resulting faults are called detachment faults. In continental interior platform region, sedimentary rock was deposited over relatively rigid Precambrian crystalline basement during the Phanerozoic. Steeply dipping fault in the basement reactivated, causing differential movement of basement blocks. This movement forces the overlaying layer of sedimentary rocks to possibly bend into the fault that drops over the edge of the basement block. Fault-related faults that form in this way are called drift faults or force faults. Shear sense indicators for brittle fault and fault zones. Offset makers. So you can define shear sense if you are able to define the relative displacement of two piercing points on opposite walls of the fault. Fault-related faults. The sense of asymmetry of fault-related faults defines the shear sense. Typically, fault interception faults verge in the direction of shear. Note also that the asymmetry of rollover faults relative to shear sense is opposite to that of other fault-related faults. Fiber sheet imbrication. The imbrication of slip fiber sheet on a faults provide a clear indication of shear sense. Fiber sheets tilt away from the direction of shear. Steps on slickened sides. Microscopic steps develop along slickened side surfaces. Typically, the face of the steps is rougher than the flat surface. However, slickened side steps may be confused with the intersection between pinnate fractures and fault, giving an opposite shear sense. And echelon veins tilt toward the direction of shear. If the veins are sigmoidal, the sense of rotation defines the shear sense. Carrot-shaped grooves. Grooves on slickened sides tends to be deeper and wider at one end and tougher on the point at the other. So those resembling half a carrot. So the direction in which the carrot points define the direction of shear. Chatter marks. As one fault block moves past another, small wedge-shaped blocks may be plucked out of the opposing surface. The resulting indentations of the fault surface are known as chatter marks. Pinnate fractures. The inclination of pinnate fractures, which with respect to the fault surfaces defines the shear sense.
Recognizing and interpreting faults. Displacement on a fault can alter the landscape. The nature of disruption depends on the type of fault, on how much displacement occurred, on the rate of displacement, on how recently faulting occurred, on the climate in the area, and on whether the fault is emergent or blind. We include climate and age of faulting in our list of factors because they determine the extent to which erosion can erase the effects of displacements. For example, in a humid climate with abundant rainfall, a fault's geomorphologic manifestation may disappear within months or years, whereas in a desert climate, a fault's geomorphologic manifestation may last for millennia. Seismic faulting along an emergent strike-slip fault typically creates a surface rupture. Surface rupture is manifested by broken ground and fissures. Displacement on an emergent dip-slip fault creates a step in the ground surface called a fault scarp. Both dip-slip and strike-slip faulting can offset topographic features such as ridges or riverbeds, and the recent fault may offset roads, fences, and sections of buildings. You can identify the trace of the San Andreas Fault in the wine district of California, for example, by offset row of casts in a wine cellar, and historic faults by offsets in ancient buildings in Greece. Displacement across regional strike-slip faults is not necessarily exactly parallel to the fault surface. in part due to the existence of restraining and releasing bends along the fault, and in part due to the relative motion of lithospheric plates during or after faulting. Transpression across a strike-slip fault may result in the formation of fault parallel ridges that may be tens to hundreds of meters high, and transtension along a large strike-slip fault results in the development of sag puns. Because of these features, the traces of major strike-slip faults are so obvious that they can be seen from space. If transpression occurs along a fault for millions of years, a mountain range develops adjacent to the fault, and if transtension occurs for millions of years, a sizable sedimentary basin develops adjacent to the fault. Many geologists, particularly those working in economic geology, petroleum geology, and hydrogeology, the field consists of the subsurface region of the crust, and field data includes drill hole logs, geophys. There are 5 evidences for subsurface faulting, and this includes the following. First is abrupt steps on structure contour maps. Second is excess section or loss of section in a drill core. Third is zone of brecciated rock in a drill core, although weak fault rocks typically do not survive drilling intact. Fourth is seismic reflection profiles, on which faults appear either as reflectors themselves or as zones which offset known reflectors. And lastly, linear anomalies, or an abrupt change in the wavelength of gravity or magnetic anomalies, suggesting the occurrence of an abrupt change in depth to a particular horizon. Changes in fault character with depth. The characteristics of a fault depend on the magnitude of displacement on the fault, on whether or not faulting ruptures a previously intact rock or activates a pre-existing surface, and on the pressure and temperature conditions at which faulting occurs. As discussed earlier, rocks become progressively more ductile with depth in the crust because of the increase in temperature and pressure. Consequently, at depths between 5 kilometers and 10 to 15 kilometers, faulting tends to yield a fault zone composed of cataclysite, whereas cataclysite forms by brittle deformation on a grain scale, and movement in the fault zone resembles viscous flow, and strain is distributed across the zone. The brittle plastic transition for typical crustal rocks lies at a depth of 10 to 15 kilometers in the crust. We purposely specify the transition as a range because rock consists of different minerals, each of which behaves plastically under different conditions, and because depth of transition depends on the local geothermal gradient. Temperature conditions at the depth around 10 to 15 kilometers are in the range of 250 degrees Celsius to 350 degrees Celsius, where plastic deformation mechanisms become the dominant contributor to strain in crustal rocks. The activity of plastic deformation mechanisms below this brittle plastic transition yields a fine-grained and foliated fault zone rock called myelinite. The degree of ductile deformation that accompanies faulting depends on the strain rate and on the fluid pressure. At slower strain rates, a given rock type is weaker and tends to behave more ductilely. Thus, rocks can deform ductilely even at shallow crustal levels if strain rates are slow, whereas rocks below the brittle plastic transition can deform brittly if strain rates are high. A given shear zone interval may therefore contain both myelinite and cataclysite, either as a consequence of variations in strain rate at the same depth or because progressive displacement eventually transported the interval across the brittle plastic boundary. At very rapid strain rates, fault displacement in rock generates pseudotachyllite. The width of a the width of a given fault zone typically varies as a function of rock strength, fault zones tend to be narrower in a stronger rock. Relation of faulting to stress. Faulting represents a response of rock to shear stress, so it only occurs when the differential stress does not equal zero. Because the shear stress magnitude on a plane changes as a function of the orientation of the plane with respect to the principal stresses, we should expect a relationship between the orientation of faults formed during a tectonic event and the trajectories of principal stresses during that event. Indeed, faults that initiate as column shear fractures will form at an angle of about 30 degrees to the sigma 1 direction and contain the sigma 2 direction. This relationship is called Anderson's theory of faulting. Anderson's theory of faulting states that in the Earth's surface reference frame, normal faulting occurs where sigma 2 and sigma 3 are horizontal and sigma 1 is vertical. Thrust faulting occurs where sigma 1 and sigma 2 are horizontal and sigma 3 is vertical. And strike slip faulting occurs where sigma 1 and sigma 3 are horizontal and sigma 2 is vertical. Anderson's theory of faulting is a powerful tool for regional analysis, but we cannot use this theory to predict all fault geometries in the Earth's crust for several reasons. First is faults do not necessarily initiate in intact rock. Second, a fault surface is a material feature in a rock body whose orientation may change as the rock body containing the fault undergo progressive deformation. Lastly, systematic changes in stress trajectories are likely to occur with depth in mountain belts. Fluids and faulting. The presence of water in fault zones affects the stress at which faulting occurs in three ways. First, the alteration minerals formed by reaction with water in the fault zone tend to have lower shear strength than minerals in an unaltered rock. Second, the presence of water in a rock may cause hydrolytic weakening of silicate minerals and therefore allow deformation to occur at lower stresses. Third, the pore pressure of water in the fault zone decreases the effective normal stress in a rock body and thus decreases the magnitude of shear stress necessary to initiate a shear rupture in intact rock or initiate frictional sliding on a pre-existing surface. Hubert-Ruby hypothesis. This emphasizes the role of elevated fluid pressure during movement on detachments and has wide applicability.
Fault systems. A group of related fault is called fault system or fault array. Although the term system and array can be used interchangeably, geologists commonly use array when talking about geometric classifications and system in the context of tectonic classifications. There are three tectonically defined types of fault system, which are the normal, thrust, and strike-slip systems. Faults in normal and thrust systems merge with a detachment in sedimentary rock at shallow depth of 10 to 15 kilometers may be referred to as thin-skinned system, while the strike-slip is a fault on which the two blocks slide past one another. If faulting involves deeper crustal rocks, it is called thick-skinned system. Geometric classification of fault arrays. Group of faults may be classified as parallel, anastomosing, and echelon, relay, conjugate, or random arrays, depending on the relationship among faults in the array and on how the faults link with one another along strike. Synthetic faults are subsidiary faults in the array that parallel the major faults, while antithetic faults are the subsidiary faults whose dip is opposite to that of the major faults. Normal fault systems. Regional normal fault systems form in rifts, which are belts in which the lithosphere is undergoing extension along passive margins, which are continental margins that are not currently plate margins, and along mid-ocean ridges. Typically, faults in a normal fault system comprise relay or parallel arrays. They can be district or planar, or contain distinct fault bands. As a consequence of the rotation accompanying displacement on a normal fault, the original top surface of the hanging wall block tilts toward the fault to create a depression called a half-graben, where most of the basins in the Basin and Range province of the western United States are half-gravens. In places where two adjacent normal faults dip toward one another, the fault-bounded block between them drops down, creating a graben. Where two adjacent normal faults dip away from one another, the relatively high footwall block between the faults is called a horst. Horsts and gravens commonly form because of the interaction between synthetic and antithetic faults in rift systems. Reverse fault systems. Reverse fault systems are commonly arrays of thrust faults that form to accommodate large regional shortening. In detail, where thrusts cut upwards through sequences of constructing strata, they have a stair-step profile with flats following weak horizons and ramps cutting across beds. An imbricate fan of thrust faults consists of thrusts that either intersect the ground surface or die out up deep, whereas a duplex consists of thrusts that span the interval of rock between a higher level detachment called a roof thrust and a lower level detachment called a floor thrust. Strike-slip fault system. Strike-slip fault systems occur at transform boundaries, which are boundaries where two plates slide past one another without the creation or subduction of lithosphere. They can also occur within plates and as components of convergent origins. Typically, they splay into many separate faults in the near surface, which, in cross-section, resembles the head of a flower. Because of this geometry, such arrays are called flower structures. Inversion of fault systems. In structural geology, inversion or basin inversion relates to the relative uplift of a sedimentary basin or similar structure as a result of crustal shortening. This normally excludes uplift developed in the footwalls of later extensional faults or uplift caused by a mantle plumes. Inversion can also refer to individual faults, where an extensional fault is reactivated in the opposite direction to its original movement. The term negative inversion is also occasionally used to describe the reactivation of reverse faults and thrusts during extension. Many inversion structures are caused by the direct reactivation of pre-existing extensional faults. The existing fault block still generally acts as a boundary to uplift and the process is sometimes known as buttressing. Fault system and paleostress refers to the determination of paleostress history from evidence found in rocks based on the principle that past tectonic stress should have left traces in the rocks. Qualitative and quantitative analysis of deformation structures are useful for understanding the distribution and transformation of paleostress fields controlled by sequential tectonic events. Deformation ranges from microscopic to regional scale and from brittle to ductile behavior, depending on the rheology of the rock, orientation and magnitude of the stress, and etc. Therefore, detailed observation in outcrops as well as in thin sections are important in reconstructing the paleostress trajectories. The stress field is assumed to be spatially uniform for a faulted rock mass and temporally stable over the concerned period of time when faulting occurred in that region. In other words, the effect of local fault slip is ignored in the variation in small-scale stress field. Moreover, the maximum shear stress resolved in the fault surface from the known stress field and the slip on each of the fault surface has the same direction and magnitude. Faulting and society. All this terminology and theory may make us forget that the study of faulting is not just an academic vocation. Faults may be studied carefully by oil and mineral exploration geologists because faulting controls the distribution of valuable materials. Regional fault analysis is required for the localization and building of large human-made structures, such as dams and nuclear power plants. Such structures, which may have devastating impact when they fall, should clearly not be built near potentially active faults. Since the most dramatic effect of fault activity in society comes in the form of earthquakes, which can be responsible for great loss of life and can destroy economic stability of industrialized countries. Faulting and resources. Faults contribute to the development of oil traps by juxtaposing an impermeable sill composed of packed gauge or fault parallel veining against a permeable reservoir rock, or by juxtaposing an impermeable unit like shale against a reservoir bed. Valuable ore materials like gold commonly occur in veins or are precipitated from hydrothermal fluids that were focused along fault zones, because fracturing provides enhanced permeability. Hydrogeologists are also cognizant of faults because of their effect on the migration of groundwater. Faulting and earthquakes. Faulting is widespread in the crust, but fortunately, most faults are inactive faults, meaning that they haven't slipped in a long time and are probably permanently stuck. But there are relatively few faults that are active faults, meaning they have slipped recently or have the potential to slip in the near future. When an earthquake occurs on one of these faults, the rock on one side of the fault slips with respect to the other. Even when slip occurs, not all movement on active faults results in seismicity. If an increment of faulting causes an earthquake, we say that the fault is seismic. But if the offset occurs without generating an earthquake, we call the slip a seismic. A seismic faulting is also called fault creep by seismologists. But why do earthquakes occur during movement on faults? Earthquakes represent the sudden release of elastic strain that is stored in a rock and can be generated when an intact rock ruptures or when asperities on a pre-existing fault snap off or suddenly blow. Rubbing two bricks while applying some pressure is a good analogy of this process. This start-stop behavior of faults is called stick-slip behavior. If we accept this modeling of faulting, fault creep occurs where a fault zone is very weak, perhaps due to the presence of weak material, hydrolytic weakening in the fault zone, or high fluid pressure in the fault zone. Geoscientists have struggled for decades to delineate regions that have the potential to be seismic. Delineation of seismically active regions plays a major role in land use planning. Obviously, the potential for seismicity must be taken into account when designing building codes for homes and when situating large public facilities like nuclear power plants, schools, hospitals, dams, and pipelines. Maps of earthquakes epicenters emphasize that most earthquakes occur along plate boundaries, but that dangerous earthquakes may also occur within plate interiors. Thus, we recognize plate boundary seismicity and intraplate seismicity. In special cases, it may be possible to determine the recurrence interval on a fault, meaning the average time between successive faulting events.